In order to help mitigate this problem of spectral leakage, we began looking at the application of the chirp Z transform to our project. The chirp Z transform is a Z transform that is performed on different points on a contour in the Z plane. If we limit this contour to a unit circle in the Z plane, then we'll be looking at the frequency content of our signal. Now, as we perform the Z transform, we're actually moving along a very small portion on the circle. As we are moving along a very small portion of the circle, it's like we're zooming in a frequency axis when we look at an FFT of a signal. So if we have a set frequency that we're sampling with and it's a fixed number of points, and if we zoom in on the frequency axis of the FFT, then it'll be like we're getting a better spectral resolution. And this is what the Z transform pretty much does when we apply to our sample signals. To get a better understanding of this, I have a little demonstration to show that it compares the fast Fourier transform versus the chirp Z transform. This demonstration looks at the spectral content of a signal, and it will show the difference between the accuracies of these two transforms. This signal that we are demonstrating is a 7.102 kilohertz cosine signal. The bottom graph is a chirp Z transform, and the top picture is the FFT. As you can see, we're actually going from 0 to half of the sampling rate, which was set for 48 kilohertz. And notice how the chirp Z transform, it actually zooms in on the spectrum right here in this area. So since we have a 7.102 kilohertz signal, we expect the frequency content that was analyzed by these two transforms to be close to this. Looking at the FFT right here, we see a spectral peak at 7.125 kilohertz, which is a little bit off compared to our desired signal. Right here, looking at the chirp Z transform, we see that it is at 7.101.6 kilohertz, which is very, very close to our desired signal. So in this case, the chirp Z transform has enabled us to get a better resolution by zooming in on the spectrum, which is, as we move along the circle and on the contour in the Z plane, we're only moving along a very, very small arc of the circle, which gives us a very, very good resolution. Also, we're applying this transform to find the phase difference of two signals. This demonstration also shows how the chirp Z transform could get a better resolution of phase difference as opposed to the FFT, as shown here. This signal was actually, this frequency was actually applied to two signals, one of which was phase shifted by the other one by 37.95 degrees. Now, this top one is the FFT signal. Notice how the phase is not exactly the same as the 39.95 degrees, whereas the chirp Z transform, it actually is spot on. Once we had some of the hardware built, we moved from simulating using a chirp Z transform to actually implementing a chirp Z transform into some of the data that was sampled using our hardware. Once we had the samples taken, we saved in text file format shown earlier in Signal Express, and we written a MATLAB script that will load up columns of these text files and perform the chirp Z transform on these samples. I'm about to show a little demonstration of some of the scripts that we have written. This script will load some of the samples taken and will show a little graph depicting of the direction of polarizable angles as we've moved around the receiving system. Quite a few samples are taken, so sometimes it takes a while, but this one is done. Now, when we perform these measurements, they were performed in an enclosed room, and we moved at about 180 degrees relative to the right antenna in a clockwise fashion with a radius of 15 feet away from the antennas, and we stopped when we were 0 degrees relative to the right antenna. As you can see here, the direction upon arrival measurements are less than optimal. is most likely be due to performing in an enclosed room where multipath can become a problem. After we viewed some of these measurements, we decided to be better testing method and move more into open areas, such as more open rooms, or ultimately outside, which is where we decide would be the best place to test our application.
All the testing to the RF system were done inside the lab, which introduced a huge issue known as multipath. Multipath is pretty much bouncing off signals off the wall. Once the transmitter was on, the receiver was picking up the desired signal plus other noisy signals which would disrupt our data. One test that we did in order to try to alleviate the problem was to test the RF system on the hallway. We were able to get better results, but the multipath was still a dominant issue.
Although the deadline for this project is over, we have a list of improvements that could be used in the case that this project were to be done by a different group or if it were to be continued. First of these improvements would be the inclusion of a phase lock loop. When we were doing the testing of our hardware, we had to recalibrate the VCO every time we turned on a transmitter, because sometimes the transmitter would be at a different frequency. So it would cause us to retune the VCO. If we had a phase lock loop, to have the VCO work at a frequency such that the downconverter signal will be within range of our sampling rate of our DAQ, this would cut our development time, because we wouldn't have to play around with calibrating the VCO each time we go into a lab. And plus, it's a much more sophisticated design as well. Also, another area of improvement that we think could be explored is the inclusion of a more sophisticated antenna array setup, and for direction pollen arrival calculations, and also exploring much more sophisticated DOA algorithms that could be used in such a project. And although this project was not the success that we had all hoped for, a lot of valuable lessons were learned in this project, and lessons that we will take into account in our professional engineering career in the future.